Number 17 in your Introduction to Electron Energy and Light worksheet. What wavelength of light does 14,000 hertz correspond to? I am given 14,000 hertz. I like to write a reminder of which variable this is attached to. This is F for frequency. I am looking for wavelength, which is lambda. Reminder that wavelength is measured in meters. A common mistake is for students to use lambda or F, those variable symbols, as the unit. So that's why I like to write down a reminder that wavelength is measured in meters. All right, so now we have to pick out which equation we're going to use. The giveaway here is the word wavelength. The only formula that has wavelength in it is the formula on the left, the wavelength formula. Wavelength is not in the energy equation, so we can't even use it. So we'll be using the wavelength formula. Now we just need to plug in what we know. C is a constant, and it's given to us. It is the speed of light in a vacuum. All light travels at the same speed, which is why this is a constant. So we're going to write out 3.00 times 10 to the 8th meters per second, set equal to lambda, which is what we're trying to solve for, times 14,000 hertz. We're now going to solve for x, or lambda, by dividing both sides by 14,000. The raw number that you should get from your calculator is 21,428.57, etc. We started with 2 sig figs. You would not pay attention to the constant because constants have an infinite number of sig figs, and we want to round according to the lowest number. 14,000 has 2 sig figs. These are placeholder zeros, and so they are not significant. So our final answer should also have 2 sig figs. Round your top 2 placeholders, or underline your top 2 placeholders and round. Your final answer should be 21,000. Take a look at what you need to measure in meters. Number 18. Calculate the energy associated with frequency 8.5 times 10 to the 8th hertz used by cell phones. We are given frequency 8.5 times 10 to the 8th hertz. And again, that's frequency. Our unknown is energy. Energy is denoted with a capital E. And remember, energy is measured in joules. So now we have to pick out our equation. The only equation that has E, energy, is the energy equation. Now we're going to go ahead and plug in what we know. We don't know E, but we do know Planck's constant. That's 6.626 times 10 to the negative 34th joule seconds times the frequency given to us, 8.5 times 10 to the 8th hertz. Plug this into your calculator, and the raw number you should get out is 5.6321 times 10 to the negative 25th. We started with 2 sig figs, so we should end with 2 sig figs. Underline your top 2 place values, then round. Your final answer should be 5.6 times 10 to the negative 25th, pay attention to your unit, joules. All right, number 19. The wavelength of a violet wave is 380 nanometers. calculate the frequency of violet light, and they also give us a conversion factor. That alone should tip us off that we need to be doing a conversion. Why? Well, wavelength, when we do the calculation, needs to be in meters. We are not in meters. We are in nanometers. So we need to convert nanometers to meters. So we'll start with what we know. 380 nanometers. Our unknown, meters. The conversion factor we're going to use, 10 to the 9th nanometers equal to 1 meter. Now we're going to set up and solve. 380 nanometers over 1 times a conversion factor. What's on top must come down. If you have nanometers on top, you need to have nanometers on the bottom. The number attached to that is 10 to the 9th. On top, you use the other half of your conversion factor, which is 1 meter. Nanometers on top cancels with nanometers on the bottom, so you know that you've calculated this correctly. Your answer for this should be 0.0000038 meters. Now that's kind of a cumbersome number with all those zeros, so I'm going to go ahead and convert this to scientific notation. So I'm going to put a number between 1 and 9.9, so 3.8. And how many times did I have to move that decimal? 1, 2, 3, 4, 5, 6, 7. Times 10 to the 7th. And because this is a small number, a decimal, it'll be to the negative 7th meters. This is the wavelength I'm going to start with. All right, reminder, wavelength. All right, the question says what the wavelength is, and we have already converted that from nanometers to meters. Calculate the frequency. So our unknown is frequency. Remember, that's attached to a lowercase f, and we measure that in hertz. So which formula are we going to use? The big giveaway is wavelength. So we're going to be using the wavelength formula. Remember, the speed of light in a vacuum is a constant. All light travels at the same speed in a vacuum. So we're going to start with 3.0. Actually, we're going to do this over here because I'm running out of room. 3.00 times 10 to the 8th meters per second is equal to wavelength, which is 3.8 times 10 to the negative 7th meters multiplied by the frequency, which is what we're solving for. To solve for this, you're going to divide both sides by 3.8 times 10 to the negative 7th to isolate f. The raw number that you should have spit out of your calculator is 7.89473 times 10 to the 14th. But remember, we want to round according to the rules of sig figs. This number, 380, has 2 sig figs. So our final answer should also have 2 sig figs. Underline your top 2 place values. Round, in this case, we're going to round up, and your final answer should be 7.9 times 10 to the 14th. Don't forget your unit. Hertz. All right, number 20 is a very complicated problem, and you can definitely expect something like this on both your flame test lab as well as your test. This is a 3-stepper. So let's start. Number 20, cell phones typically operate at a wavelength around 35.29 centimeters. calculate the energy of the radiation used for cell phones, and they give us a conversion factor. All right, so we are given centimeters, which is great, but remember, wavelength is only measured in meters when we're calculating with it. So we need to convert centimeters to meters. What are we starting with? We are starting with 35.29 centimeters. This is my wavelength. I'm trying to get to meters. And the conversion factor I'm going to use was given to us. 1 meter is equal to 10 to the second centimeters. Plug in what we know. Start with 35.29 centimeters over 1. Multiply by a conversion factor. What's on top must come down. We know that centimeters needs to go on the bottom. The number that's affiliated with centimeters is 10 to the second. If we use 1/2 of our conversion factor, we have to use the other half on top. Multiply your numerators together and your denominators together, and then divide the top and bottom, and you will end up getting 0.3529 meters. This is your wavelength that you will use at your start. So 0.3529 meters. Reminder, this is our wavelength. What's our unknown? Well, it's asking for energy. So which formula are we going to use? Well, we have wavelength and we have energy. Oh crap. Now what? Well, we know that if it says wavelength, we have to use the wavelength formula. And if it says energy, we have to use the energy formula. So this is a case where we actually have to use both. Here's why. In order for us to get from wavelength to energy, we have to calculate frequency and then use the value of frequency to plug into the energy equation to then get energy. It's a lot. So our unknown in this case is not going to be energy. It's actually going to be frequency. And remember, we measure that in hertz. So we're going to be using the wavelength formula. Plug in what we know. The speed of light in a vacuum is 3.00 times 10 to the 8th meters per second. We have the wavelength, that is 0.3529 meters times frequency. Divide both sides by 0.3529 to get F by itself. The raw number that you receive on this side is 850 million, 99,178.2 hertz, because that's what we were looking for. Do not round this number. You are going to round at the very end. We are going to use this number up here. All right, so our start is 99,178.2 hertz. Reminder, that's frequency. Our unknown this time is energy. So we're going to be using the energy formula this time. Plug in what we know. We don't know energy. Oh, also, remember, energy, that's the capital E, is measured in joules. Don't forget. E equals Planck's constant, which is 6.626 times 10 to the negative 34th joules seconds times, and I apologize, I'm going to run out of room here, so I have to wrap around, 850,099,178.2 hertz. Multiply those two values together, and the raw number that you get is 5.632757 times 10 to the negative 25th. But we need to round according to the rules of sig figs, so take a look at what we started with. We started with 4 sig figs. So we want to end with 4 sig figs. Oops. That's quite ugly. 4 sig figs. So underline your top place values, 1, 2, 3, 4, and then round. In this case, we're going to be rounding up. So your final answer is 5.633 times 10 to the negative 25th, and the units, remember, are joules. And that's the final answer to question number 20.